So let's discuss this different way of graphing vapor pressure and temperature data. What we'll introduce here is the Clausius-Clapeyron equation, and this is simply a different way of graphing the temperature dependence of vapor pressure. So recall the graph of the vapor pressure versus temperature plot for acetone and water in a previous slide. I've reproduced it here. So we have vapor pressure in torr versus temperature in Kelvin for both acetone and water. Now, if instead we graph the natural log of the vapor pressure, so I have as ln of P here, and on the x-axis, instead of graphing Kelvin, we graph 1 over Kelvin, or 1 over T. What we end up with is a graph that looks like this. So what we've done is, again, instead of plotting vapor pressure versus temperature, we plot the natural log of the vapor pressure versus 1 over the temperature. And what we get are two straight lines, one for acetone and one for water. For acetone, the plot of ln of P versus 1 over T results in a straight line with a slope equal to minus 3731.3, happens to have units of K, and a y-intercept of 17.946. For water, the ln of P versus 1 over T plot results in a straight line with a slope of minus 5169.9 and a y-intercept of 20.5. So note the slope of the line for water is more negative than the slope of the line for acetone. Now, for reasons that I want to take the time to discuss, the term ln of P will have no units. Therefore, the units of slope are K. And so you might ask, why are we graphing the data as natural log of the vapor pressure versus 1 over T? Well, I'm glad you asked, because we can use a plot like this to get an experimental number for the enthalpy of vaporization of each liquid. Let's look at what we mean by the Clausius-Clapeyron equation. Basically, this equation has this uninteresting form. The natural log of the vapor pressure is equal to minus the heat of vaporization divided by the universal gas constant times the absolute temperature plus a constant. So of course P is the vapor pressure, delta H VAP is the enthalpy of vaporization in units of joules per mole. The gas constant would be the gas constant in units of joules per mole per K. The temperature, of course, is in Kelvin, and of course C is a constant. Well, if we rearrange this equation a little bit, we can make it look a little bit more like the equation of a straight line. So you see I've broken out the 1 over T term here, and so we have this equation in the form of y equals mx plus b, where of course y is the natural log of the vapor pressure, x is 1 over T, and m is the slope, is equal to minus delta H of vaporization over R, and the constant C is simply the y-intercept. So this means that if we make a graph of the natural log of the vapor pressure versus 1 over T, that graph should be linear, and the slope of that line is equal to minus delta H of vaporization over R. So we can get the heat of vaporization from the slope. So let's use the equation of the line for each of the plots for acetone and water that we saw on the previous slide to calculate the delta H of vaporization for each substance. So what I have here are two boxes: on the left acetone, on the right water, And these are the equations of the line that we obtained on the previous slide. So for acetone, the slope of that line was minus 3731.3 K. So I've written that here, and we recall that the slope is equal to minus delta H of vaporization over R. So what I'm simply going to do here is algebraically solve for delta H of vaporization. We put in our number for R, 8.314 joules per mole per K. We're going to cross multiply here. We end up with the negative delta H of vaporization equal to the negative 3731.3 K, the slope, times the gas constant. Of course, we have negatives on both sides, so they cancel out. We solve for heat of vaporization, and we get 3.1 times 10 to the fourth joules per mole, which I'm going to convert to kilojoules per mole. If we do the same calculation for water, what we get is 43 kilojoules per mole. Turns out that each of these values are in good agreement with values reported previously. So we saw a value reported previously for acetone of 31.3 kilojoules per mole, compares well, and water had a range of values listed before from 40.7 to 44, and our number from our plot is in good agreement with that. So the take-home lesson here is that if you can measure the vapor pressure of a liquid at various temperatures, you can obtain the enthalpy of vaporization, or the heat of vaporization, delta H VAP, from the slope of a plot of the natural log of that vapor pressure versus 1 over T. T has to be in Kelvin, according to the Clausius-Clapeyron equation. Let's look at an example of a different liquid than acetone or water. Dimethylsulfoxide, which is known as DMSO in research labs, is a polar solvent with a high boiling point that is oftentimes referred to as a universal solvent. It's a favorite in research labs that need solvents to dissolve compounds that don't go very well into either water or other common organic solvents like acetone or ethanol. DMSO is also miscible, or it's soluble in water. Now suppose the vapor pressure of DMSO vapor in equilibrium with the liquid is measured over a range of temperatures. We have some data to the right. Notice the temperature gets quite high since DMSO is not very volatile at room temperature. So at even 150 degrees C, the vapor pressure is only 238 torr. So what we want to do is use this data here to determine the delta H of vaporization for DMSO. Now, before we can use our Clausius-Clapeyron equation, we're going to need to do a little work. And that work will involve finding 1 over T and the ln of P. So what we've done here is we've taken these two yellow columns of original data, reproduced it here. So here's the temperature in degrees C and the pressure in torr. And we realize that in order to make the Clausius-Clapeyron equation work and plot the data correctly, ln of P versus 1 over T, we need to change the degrees C to Kelvin, and then we need to take the reciprocal of those Kelvin temperatures, and we'll take the vapor pressures and take the natural log of each of these vapor pressures. And you'll notice that I've been a little generous with significant figures here. If we plot this data, again, what are we plotting? We're plotting the natural log of the vapor pressure on the y-axis. We're plotting 1 over the Kelvin temperature on the x-axis. We have 5 points. 5 points are these blue dots here. We've added a trend line in Excel, told Excel to show the equation, and here's the equation of the line for this data. We can use then the Clausius-Clapeyron equation to calculate the heat of vaporization. The slope of this line is minus 5993.2 K. We set it equal to minus delta H of vaporization over R. Just like we did for acetone in water, we solve for the heat of vaporization, and we convert the final units to kilojoules per mole, and we get 49.83, and that number is higher than either the number for acetone or water, which is consistent with the fact that DMSO is much less likely to evaporate at any given temperature than acetone or water. DMSO would be less volatile than acetone or water. It's quite hard to evaporate. Let's look at this a little bit more. How about if we try to use the data in our table to determine the normal boiling point of DMSO? Remember, that would be the temperature at which the vapor pressure of DMSO equals normal atmospheric pressure, or 760 torr. Well, we have a problem here in that our data, even at 150 degrees C, the vapor pressure of DMSO has only reached 238 torr. So we don't know how high we need to heat, what temperature we need to heat the DMSO to for its vapor pressure to equal normal atmospheric pressure, or 760 torr. What we could do is we could basically extrapolate the line that we drew on our graph so that the vapor pressure was 760 torr. Another way of saying that is that we can use the equation of the line for our graph to try to get the normal boiling point. And here's how we go about doing that. Here's the equation of the line for the DMSO plot on the previous slide. And of course, y is the natural log of p, and x is 1 over t. And what we're going to do is set y equal to 6.633. Now, why would we do that? Because what we want to do is we want to solve for t when p is 760 torr. And the ln of 760 is 6.633. So we want to know what's t when y here is 6.633. So we have 6.633 equals minus 5993.2x plus 19.665. I'm simply going to solve for x here. When I solve for x turns out to be equal to 0.00217,446. Again, I'm being a little sloppy with significant figures here, at least in the intermediate calculations. You have to remember that that's not the temperature, that's 1 over the absolute temperature. So if the 1 over the absolute temperature is this number, what we need to do is take the reciprocal of the number to get t, and t turns out to be 460 K, or 187 degrees C, and we can compare that to the accepted boiling point of DMSO, or 189 degrees C. Well, some interesting things to note about DMSO, besides its heat of vaporization at a very high boiling point. The 2D Lewis structure of DMSO looks like this, and you might note that this looks fairly similar to acetone, only in acetone, instead of a sulfur there, you have a carbon. This would be a 3D ball and stick model of the same molecule. Now, DMSO is not only miscible or soluble in water, but strangely enough, pure DMSO liquid absorbs water vapor right out of the surrounding air. In other words, it's what we call hygroscopic. Also, the freezing point of DMSO is quite high. It actually freezes at just under 20 degrees C, which is around 65 degrees Fahrenheit. So it cannot be used as a liquid solvent for reactions under this temperature. I remember one time receiving DMSO for my research lab, and I took out the bottle and it had solidified. Well, what happened? Well, it was delivered in the winter. It had been sitting out, got cold, and it froze. So I had to thaw the DMSO at room temperature in order to use it. The other thing about DMSO is that it's readily absorbed through the skin. Therefore, if you use this solvent in the lab, you need to wear gloves.